Hello, I'm Hugh Manfield and welcome to my science channel. Now, as I've said before, you're going to hear things on this channel that you won't hear anywhere else. So if you're tired of hearing the same old thing rehashed and reconstituted on other video channels, you've come to the right place. This is the only place you can learn about fluid space theory, other than my book, Einstein and Aliens, which is available on Amazon.com. And today I'm going to be talking about something that probably no one else has brought up yet or even will bring up. And that is that there's a recent study that came out this year that has challenged all of the major theories of the universe. The Big Bang, general relativity, dark matter. All of these have been brought into question by this study. Well, which study am I talking about? I'm talking about Tobias Mistel and the Case Western Reserve study on the long-range rotation curves of galaxies. This study is said to have dealt a blow to the current theory of dark matter, but the implications may go much further than that. A long-standing question of mine has been, at what point do we see Hubble expansion, the expansion of the universe, begin to affect the orbits in bodies that we can observe, like galaxies, galaxy clusters, etc. Basically, the situation is what I have here on this chart. Now, this is for our sun at radiuses of 100 AU and greater. And you can see the gravity, the acceleration of gravity from our sun out at this distance is very small, like some order of 10 to the minus 7th. But that's bigger than the expansion rate. But as you move away from an object, the gravity decreases, and we see this in the blue curve, until we get out to about 1000 AU, and it is very small. However, Hubble expansion, on the other hand, is always increasing. So the farther you go away, the greater effect it's going to have. So eventually, with gravity decreasing and Hubble expansion increasing, you ought to reach some point at which gravity loses the fight to expansion. You'll either see orbits being lifted and slowed as the pull of gravity is countered by the outward force of expansion, or you will see objects becoming detached altogether. So my question has been, when does this happen? I mean, we've all heard about the Big Rip. As the universe continues to accelerate in expansion, pretty soon galaxy clusters will be pulled apart, then galaxies themselves will be pulled apart, and then planets will be pulled away from their solar systems, and then planets themselves will be pulled apart. Okay, well, when is this going to happen? I've never seen anyone put a number on it. Like, at what expansion rate will we see stars being pulled away from galaxies like the Milky Way? So that's the question I would like to answer. So I set about trying to answer that question, and at first I started looking within the solar system. Is there an effect of Hubble expansion within the solar system? And I asked the people at Jet Propulsion Laboratory, and they said, no, we don't see any effect of Hubble expansion within the solar system. In fact, out of the orbit of Neptune and beyond, over a 100-year period of expansion, an object would only be displaced outward by about 60 to 100 kilometers, depending on how far out it is. And that's a very small amount. I mean, if you can locate an object out past Neptune within 60 kilometers, you're doing pretty darn good. So at Jet Propulsion Laboratory, they say we don't have to account for expansion when we calculate orbits. And then I asked them, well, where do you think we would have to account for expansion in calculating orbits? And they said, well, our job is to track objects within the solar system. We don't do theoretical physics. And they don't. And they do track objects very well. So they don't need to account for Hubble expansion to do their job. So where else was I going to turn to try and find an example of where you would have to account for Hubble expansion in the calculation of an orbit? Well, at Princeton, they do some very nice galactic modeling. And I asked Dr. Jeremiah Ostraker some questions. He was kind enough to respond to some inquiries I made about his book, Heart of Darkness. And it's a very dark cover, so it's probably hard to read. And one of the questions I asked him was, do you account for Hubble expansion in your galaxy models? And basically his answer was, no, all you need is dark matter and Newton's laws. So at the galactic level, you still don't have to account for Hubble expansion on the orbits of stars. So I ran a few numbers myself, and for the Milky Way, it's about 14 kiloparsecs in radius. So I ran the numbers at 15 or 16 to be generous, and that gives you a Hubble expansion rate of about 1 kilometer per second or 1.1 kilometers per second. And the rotation curve of the Milky Way, the stars at the fringe, are moving at around 240 kilometers per second. So 1 kilometer to 240, well, that's less than 0.5%. It's a very small amount. So even if it did have a tiny effect, we probably wouldn't notice it. So for galaxies, they're right at Princeton. You don't have to account for Hubble expansion. Well, at this point, I was kind of at a loss, because where am I going to look now? Where is there data about large-scale systems and orbits? And when I thought about this study and read it through again, it occurred to me that this is a good place to look for the effects of Hubble expansion on an orbit. So I ran some numbers, basically just using circular kinematics, Newton's laws, to come up with some idea about how does Hubble expansion compare to the forces of gravity on this scale. Hubble expansion is easy to compute. You take the Hubble constant, and I use 70 kilometers per second, which is the same that they used in their paper. And at 100 kiloparsecs, of course, you're going to get 7 kilometers per second of expansion. And increasing linearly outward till at 800 kiloparsecs, you're going to get 56 kilometers per second. So how does that compare to the acceleration of gravity? Well, I calculated the acceleration of gravity based on the acceleration that required to move an object around an orbit at 200 kilometers per second and these distances. And I got some very small accelerations on the order of 10 to the minus 14th up to 10 to the minus 15th. So these accelerations are 15 to 16 orders of magnitude lower than the Hubble expansion rate. Now, normally in physics, when you have two inputs into a system and one input is 16 orders of magnitude greater than the other, you dismiss the smaller one and you focus only on the big one. But in the case of orbits and galaxies, we dismiss Hubble expansion and we focus only on the input that is 16 orders of magnitude smaller, the gravitational acceleration. Something doesn't quite seem right about this to me. So I know what some of you may be saying. Well, you're comparing apples to oranges. You're comparing a velocity to an acceleration, and they're two different things. And that's true. So I ran the next set of numbers to try and figure out how long will it take for the acceleration to overcome the expansion rate. Because given enough time, objects can be accelerated, even at a tiny acceleration, to very high velocities. At the acceleration rate at 100 kiloparsecs, to reach 7 kilometers per second will take something like 16, 17 million years. At 200 kiloparsecs, it takes almost 70 million years. And that number keeps getting bigger and bigger until out at 800 kiloparsecs, to accelerate an object up to 56 kilometers per second at the acceleration rate of the gravity would take almost 1.1 billion years. So this is a very long time for gravity to have to catch up to expansion. I mean, it takes 1.1 billion years for gravity to do what Hubble expansion does in each and every second of that 1.1 billion years. So it's starting to look like at least there's a chance to see the effect of Hubble expansion on orbits at this scale. But to make more of an apples to apples comparison, I did a simple vector analysis. I took the velocity vector of the orbit at 200 kilometers per second and plotted it in blue at all of these various radiuses, and I extrapolated the data out to 1 megaparsec, which is consistent with what they do in the paper at Case Western Reserve. And then I calculated the Hubble expansion vector and plotted it for each of these radiuses out to 1 megaparsec. And then I did simple vector addition and came up with the resultant of those vectors. And as you can see, within this range, objects in orbit at this velocity will be increasingly diverted from their orbital path. It amounts to only a couple of degrees in here at 100 kiloparsecs, but by the time you reach 1 megaparsec, the diversion is almost 20 degrees. So this looks like a pretty sure effect that Hubble expansion is going to be pulling these objects away from their orbits, either lifting the orbits or slowing the object, and we should be able to see that. Here's another chart from the paper. This one's showing a galaxy with a rotation curve at around 200 kilometers per second, and the various data that was used to arrive at that, extrapolated out to 1 megaparsec. And the thing about this chart is it shows this green line, which is the predicted dark matter curve, which was expected to decline with distance. But they didn't see that decline. They saw flat galaxy rotation curves going on indefinitely. So the point of this chart is that when you add Hubble expansion into the mix, it's even worse for the dark matter curve because the orbital velocities were predicted to be slower, giving Hubble expansion an even greater percentage of the orbital velocity and created an even greater diversion angle from the circular orbits. If you think it's bad for this case, it's even worse for the predicted case using the old dark matter models. Just to be complete, I looked at some galaxy clusters, and I looked at the Virgo cluster, which may not be the best choice because it's a fairly compact and very dense cluster. So if you looked at larger clusters with fewer galaxies, you might find an even greater effect. But what I found is that Hubble expansion is about 5% of the orbital velocities in the Virgo cluster, which isn't much, but it should be noticeable. You should be able to notice a 5% lifting and slowing of orbits, and we don't see that. So this brings me to a topic that I like to discuss, and that is, what is science fact and what is theory? I mean, if you read blogs online and watch videos, you can see that Hubble expansion is described as a fact. It's something that they truly believe is happening. The Big Bang is reported as a fact. Everyone believes in the Big Bang these days. So all of these have become ingrained and presented as facts in one way or another in different articles and videos. Well, what's the truth about it? Well, the truth is only one thing from that list can be considered a fact, and that is that we observe a cosmological red shift with distance in the light coming from galaxies. All the rest of it are theories that have been built on top of that cosmological redshift in an attempt to explain it. But, like I said, if you read and listen to some of the articles, they don't even talk about redshift. They talk about measuring the speed galaxies are moving away from us, which is an assumption based on a theory. They talk about measuring the Hubble constant, which is also an expansion rate, which is an assumption based on a theory. Now, you may say, well, yes, but we've checked these for years and years, and everything checks out. It's got to be true. No, it's still a theory, and you've got to be able to keep your distance from your theories and not let your theories become a belief system. However, within physics, I think, sadly, that is exactly what has happened. A lot of these theories have become belief systems. So then, when you try to challenge that theory, you're challenging someone's belief system, and they react emotionally, which is not good for science. Based on what I've seen, we should see some effect of Hubble expansion on orbits around isolated galaxies at these distances, and we don't see it. These are observations. This study is based on not just a few observations, it's based on a lot of statistical data from thousands of galaxies that have been sifted and sorted into the right categories and then averaged together to come up with these curves. And they sorted them by galaxy type, galaxy mass, and they only selected galaxies that were viewed edge-on so they could get good data. And from reading the paper, the data seems very solid. We can count these orbits as an observation. Now, what does theory say? Theory says that if Hubble expansion is actually happening, we should not see these orbits. Okay, so I go with the observation, which then raises the question, then Hubble expansion, if you don't have to account for it, that must be because it's not actually happening. Now, to a lot of people in physics, those are fighting words. Hubble expansion not happening? Are you crazy? There's a cosmological redshift, and it's the only possible explanation. Well, no, it's not the only possible explanation. In fact, with signs like these, that Hubble expansion is not actually happening, it's about time to start looking for another explanation. So what if I'm right? What if this study not only shows that dark matter doesn't exist as conceived, it also shows that Hubble expansion, the expansion of the universe, is not actually happening as currently conceived? What's going to happen to all these theories? Well, all of these theories are built on the observation of cosmological redshift. And as such, if Hubble expansion isn't happening, then the Big Bang comes into question. General relativity supported the Big Bang. It comes into question. Dark matter's already been called into question by this study. So basically, all of modern cosmology goes out the window. That is a big problem for physics, and no one really wants to admit that it exists. But is it possible that everything we've been taught, everything that we've been told, everything that we think we've learned over the last 100 years is wrong? Well, if you ask me, I say, yes, it probably is wrong. And that's something to think about. So until next time, I'm Hugh Manfield.